Alright, so we're just going to do a video and explanation as to why the SVP64 loop prefix is independent of the defined word instruction that it is prefixing, and it's to do with multi-issue, parallel multi-issue decode. Right, so first a couple of things. One is that when we say SVP64 prefix, we are not referring to the P09. The P09 front preamble. There are 2 bits here, and that follows up with the 24 bits. So this is the SVP64 area. So this is when we say SVP64 prefix, we're talking about this. We're not talking about this. Okay, that's 24 bits. This is alright. So when you're doing SVP64 identification, you'll be looking for the pattern binary 001001 01, and when you see that pattern, you know that it's a 64-bit prefix, and that is very easy to identify in parallel. And so what you can do is you can use, you've got a sequence of bytes in a multi-issue context, a sequence of words, in multi-issue context. Using this as the identifier, you can work out the length of its P09. Let's just say it's that one, okay? Then, using carry propagation, you can work out in an order n squared gate delay. It's basically this order n squared on this. Right, what about these? Okay, so let's have lots of them. Let's say we do 6. All right, 6-way multi-issue, and we have a decoder for each of these. So in parallel you can start doing this. So you also do is this P09? Is this one 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 P09? That's done in parallel. And you also decode it as a, so let's say it's this one is P09, and let's say that one is P09. Alright. And this one is, say, add I, but we don't know that yet, and this one is mul I, let's say that one is SC. I deliberately picked that one because it's unvectorizable. And this one is, let's say, SRADI. Alright, now, this one, SC, that can be identified as 32-bit and decoded as SC. Alright. This one gets decoded and identified as SVP64. Right. This one is 32, but I think it is an add-I. Right, remember, this is being done, all this is being done in parallel. 32, add-I. This one's identified as SVP64. And this one is being decoded at the moment as 32-bit. That's SRADI. Okay, now every single one of these is completely independent. Right. There's no back dependency, no dependency on the previous byte. There's no dependency on the next byte. No dependency on the previous word. No dependency on the next word. Now, having done these, let's SC, having identified these 32-bit defined words, this one is SC, this one is add-I, this one is add-I, and this one is SRADI, oh sorry, MALI. Within these, you can start immediately identifying the immediates. All of the immediates for that, and that, and that were decoded perfectly fine in parallel. Now, here is an SVP64-Prefix, and here is an SVP64-Prefix. Now, using that carry propagation system, using carry propagation, you can work out that this is 64-bit, and that is 64-bit, and that one was 32-bit, and that one was 32-bit. But in parallel, you're still, in parallel with identifying where the length starts, you are still independently decoding these without referring to prefix or to the instruction after it. So again, it is entirely this bit up to here was entirely independent. Now you go, oh, actually, we've identified now where the start of the 64-bit instructions are. Sorry, not 64-bit instructions, the prefixed instructions, because in SVP64 there are no there are no 64-bit instructions. Okay. Now you can pass this over to the decoder involving prefix decoding. Alright, so you've already got the immediates from here, and those carry down, but at this point it branches out again into parallel decoders or an execution. So this would be, in your multi-issue out-of-order system, this would be farmed off into register hazard management straight away. And this one be also farmed off into hazard management. Whereas this one, a little bit annoying, but you need to unpick our RT and RA and back depack some of this. Okay. Back unpick some of this, so it becomes vectorized RT, vectorized RA, vector RT, vector RA, and there are within the SVP64 area there is some identification of identification bits, and rather annoyingly you do actually have to know what this is before you can decide which bits. So you do actually have to do a partial decode of the partial identification of the instruction. It doesn't have to be a full decode, but it does have to be enough to know where the where the extra bits, as they're called, which extend the numbering of these and identify whether they're scalar or vector. But that's the only augmentation that occurs there at this critical decode phase. So now you've got your regs, and you can do the hazard management there. Alright, so let's to recap. Firstly, this entire P09 area is not dedicated to SVP64. They are not the same thing. You have this tells you, this pattern tells you whether the length is 32-bit or 64-bit. If you see that pattern, you know you have a 64-bit encoding. You can then, in parallel, you can use a carry propagation algorithm to identify the starting position of every single one of the 32-bit word instructions and the starting position of anything that is 64-bit in length. But you can start the decoding phase of every single one of these without throwing away what is used here, what is created here, and what is decoded here. Now, let me find a page. Let's say we decide to, within that prefix area, P09, this is a 2-bit area, and that's SVP64. Let's say that we decide instead that some of these bits in here, where previously we had a nice simple pattern, let's say that some of these in here are used for other things. Right? Let's say right, it's complex. I'm trying to think of an example. Right, let's say that you pattern the pattern 10101010. Sorry, 101010 is a completely different instruction, right? Where the previously it was completely orthogonal, you now have to do, you have this and this. Okay, right. 1, 2, 3, 4, 5. Right, let's just do 5. I'm going to find another pen. Okay. Right. So you got your. Now, basically what you have to do now is you have to look explicitly for this pattern. So you have to, for this parallel decoder, it has to take that and that. For this parallel decoder, it has to take that and that. For this parallel decoder, it has to take that and that. For this parallel decoder, it has to take up with that and that. You have to start, and you can ignore this one. So now you have to do 2 sets of decoding, right, of entire 64 bits overlapping. You can see where this is going. It's going horribly wrong already. Right? So where previously it was nice and simple and straightforward, every single one of the things could be done in parallel. Now you have to spot this pattern here, right, which is 0 0 1 0 0 1 1 0 something and 1 0 1 0 1 0. Yeah, and this one as well. You're looking for that pattern in here, and if you see that pattern, which is horribly complex, right, especially if you have multiple instructions, let's say you also add 0 0 0 1 1 1, you've also got to look for that 0 0 1 0 0 1 1 0. That's within the 32-bit, the first 32-bit word, and then the other one was 0 0 1 1 1, etc. You now have to look for that pattern. You've now introduced additional gate delay on here, and bear in mind that this is the length decoding we're talking about. So instead of a very simple process here, right, where in parallel you were identifying the length at the same time as performing the decode, the 32-bit independent decode. Now you have created a situation where you can begin decoding these, but in some cases this is going to be gobbledygook. Right? You literally catastrophically poisoned and destroyed the ability to use efficient risk paradigm multi-issue decoding, because once you've identified this pattern, then you know that that pattern is 64-bit. But it's a horrible number of gates involved, and the more instructions you add to this list of exceptions that go into here, the greater the latency involved in identifying whether the instruction was actually 64-bit or 32. You have no idea where the instruction starts. And that was what happened. That's basically what happened with Intel. And their solution was awful. They basically did speculative. Basically, this is a nightmare path doing this. They did exactly this. They have no idea if it's a 32-bit or a 64-bit encoding, so they speculatively decode both, and only when you get halfway through, once you identify the length, do you start chucking away the things that you eventually discovered weren't in fact 32-bit, but were 60-bit. Sorry, that weren't in fact 64-bit, but you get the idea. You can't do it. Intel cannot get 100% throughput in their multi-issue cores. They cannot go to, for example, 16-way multi-issue. You just can't do it. As you have to, because you've got too much on the this only works because it's a simple carry propagation algorithm, right? For identifying the thing, that's to look for that pattern. That's one or two gates, put it into the carry propagation algorithm. I mean, it's an extremely efficient and elegant thing, but you can't delaying it. You have to push that to later, and it potentially pushes it, because remember, these decodes, decoding of these the scalar instructions alone is already extremely complex. We've got 4,000 gates for decoding the operand fields here, and that's just in the SFS subset, 150 instructions. We've really got to watch the gate latency on this, and not even being able to identify the length until after you've done a identification of some of these 64-bit patterns. Yeah, so you can do speculative decoding of this, and then down the line, once you've done this, halfway down here, bring that in to the identification of whether it's (64-bit or 32-bit). So we can't do it. Thank you.